Okay, so let us look. So we need to figure out what we need to return. If we return first, we will know what? What will we know?
We will know how much of the sequence we've consumed, but we wouldn't know if we've consumed the whole thing.
We wouldn't even know if we found something or not.
That too. Mm-hmm.
We just wouldn't know. You have a pointer. Whether the pointer reached the end or not is not clear. It isn't. Right? So now let us figure out what we need to return. And it's very simple. Look at our state now. It's typically return. If you know something, return it. The client will figure out what to do with it. Here in particular, the client will be able to see if we either reached the end or we found what we're looking for. Right? So,
can they just run the predicate again on the result?
Can you? What if you are at the very end? Then you cannot even have no right to dereference. You see, this is a guard. Think about very simple C array. You keep dereferencing, then at the end, there is nothing there. There is this, the computer will melt. The end of May, I don't know what will happen. You always have to use the guard. But if I didn't return the guard, which in this particular case, n, you don't know. You really don't know. Right. I usually put space here. I don't know why, but just. Okay. So I think we're good. So I don't know what is this. That should have, in my computation, that should have been the last thing we work on. Oh, I see. Oh, yeah. This is fine. This is fine. There's this guy. I apologize. I forgot what we're doing. Okay. Now, remember that we are still struggling our path to binary search. And what I claim that in order to see what's the correct binary search, how to do it, we need to reduce it to a simpler problem. Say, how could we reduce binary search to a simple problem? Well, binary search, however you look at it, sort of deals with two things. First, with a monotonically non-decreasing sequence. First. Second of all, with some predicate which allows you, with some binary predicate, which establishes strict weak ordering on this sequence and which allows you to compare elements. This is too much. This is why, even people who design API, even people as good as Dennis Ritchie, make mistakes. This was, according to my sources, Dennis Ritchie interface, bsearch. Yes? So let us see what's the simpler problem. And what I claim that the simpler problem than sorted sequence is a notion of a partitioned sequence. Remember, I was promising partition. Here, partition comes from a different sort of path. Before we learn how to partition, we need to come with a notion of a partitioned sequence. Sequence is partitioned if good guys precede bad guys, or bad guys precede good guys. Right? So, sequence is partitioned according to what?
A partition function.
A predicate, yes. So you need a predicate, and the sequence is partitioned if
everything in the sequence returns true first and then false later, or the other way around?
That's an interesting question. What's the right answer? This is a very tricky thing, and that's where, by the way, STL gets it wrong.
I mean, if we take less than as the canonical predicate, then is that not the canonical predicate?
That is not, I mean, your predicate is good. Unary predicate. You look at something, good guy, bad guy. I didn't mean, it's just an example. But, whom should we put first? And let me tell you, when I was doing STL, and I was very young, inexperienced, naive guy of 43 years old, whatever I was at the time, I thought that good guys naturally should come before the bad guys. And that's what STL does. It puts guys satisfying the predicate. Because satisfying is good. Don't you want to have satisfying things? Yeah. So I put good guys first. Why? No, not quite. Thank you. Thank you. We want partition sequence to be sorted on the Boolean values, and since STL assumes that ascending order is the natural order, most people do. There I had a choice, but I picked the natural thing. I had to make partition consistent. So I did not. This, I have to just say that I made a mistake. I realized that it was a mistake very soon. But changing something in the standard is impossible, whatever arguments you give them, because they just don't listen to arguments. They say, it's the standard. So in any case, so what I'm going to do, I'm going to ignore STL and do things correctly, because they'll just work better throughout the rest, yes? So, but it is, it is a very embarrassing mistake, and there is something to, I think one of the lessons of this particular lecture is how hard are simple things. Right? We see, like when we looked at copy n, we see lots of very bright people cannot give it correct interface. We look at B search, we see brilliant people make mistakes. And not just, again, there's lots of people who implement binary search in textbooks incorrectly. Why? Because it's hard. Simple things are hard. So let us look at the partition and let us try to figure out how let's implement a simple function called isPartitioned. Because we will need it as a precondition for something else. It's not a very useful function practically, but it's a good function as a precondition. And it will show that we actually already done the work. So let us try to do isPartition for a bounded range. Could we do that?
First we do a find if to find the first true guy.
Yes.
And then we do a find if not.
You need a predicate.
Well, we need a predicate.
Yeah. You have a predicate. That's the predicate. So you first do find if. You skip over all the false guys. And then you do find if no. 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 Find if not.
And if that is not equal to last, then it's not partition.
Yes. So it's a very simple sort of, it should be inlined because it's basically just nested. Could we write it? So observe that sort of preconditions here, by the way, we could have just literally copied any of these guys because both type requirements and the precondition is the same. Guys, I meant to say it and I forgot, and I was misleading you for about an hour. Let's go to our first function and observe that in this function and in every consecutive function there is one type requirement missing. I should at least look at my notes. That would help. What is the type requirement which is missing there? Yes, this has to be an input iterator. That has to be unary predicate. Should there be some relation between them, guys?
Oh, the star I has to be the domain
Star I returns what?
the value type of the iterator should be the domain of the predicate.
Argument type of. So that's the requirement which we need to put here, that value type of I
equals the argument type of P.
right? And it goes, by the way, in all of our functions. We just missed it. And just to prove that it's just my stupidity. What? Well, in the standard convertible, in my class equal. Just, I want to. Yes, I wrote it, guys. But sadly enough, I forgot. Obviously, everywhere else, but that does need to be done now.
So now we do first equals.
By the way, the same thing applies here. Right? And the same, by the way, the same precondition. Should be a valid range.
So first equals find if first last pred.
I would say return. Before you do anything else, I'll say return. Because you are ready to return. Well,
Find not if, find if. Okay, you can do that, but it's convoluted. Then you'll say
last.
I was going to do it in 2 lines, but if you insist. Last equal find not if, find if not. And then the first argument there is find if. First last spread. That should do it. Semicolon.
Now, since we will need it, let me torture you a little bit. What about if we deal with counted range?
Then we do need 2 lines, I think.
We don't really need 2 lines, but how will it change? Let us write is partitioned n.
All right. Cut and paste. Okay, so we'll call them twice, and in the end, n has to be.
We call them, both put suffixes n, and then you have to remember that now find if n, and by the way, we need to write find if not n, which we forgot. True, yes, it's straightforward.
But there's no way to, take a pair and interpolate it into the arguments of a function that I know of.
You want the first argument.
Yes. There is no, how did I do it?
In Python you could, but
In Python you could, yes. Or Dijkstra could in any language. Because he believed in, yeah, I did it the way you're telling us, yes. I actually did it with 3 lines. Because I need it twice.
Right. So standard pair, yeah.
So we found, now we need to restart it. So the way you could just repeat P, you don't need to declare it again.
Yeah, and then to P dot first, P dot second in the arguments to find if not N.
Yes? So, no.
I mean P dot second equal 0.
Yes. If it's equal 0, then we're good. Yes, it is partition. Now, when we do this partition thing, observe what we have. We have a partitioned range which starts with bunch of false guys. These are false guys, followed by true guys, right? There's always one special point in a partition range. Only one. The partition point. That's the point. When we actually literally even have an algorithm for finding partition point. Now, what is this algorithm called? Never mind low bound. I'm talking, we just wrote. Find if. Find if actually finds the partition point. Except it's a bad algorithm for finding partition point. Why is it bad algorithm? Does too many predicate applications. We could do better if our range is at least forward iterator range. Okay? Observe that with inward iterators, we could do nothing. We couldn't go to the middle, test, and then look back. The things disappear after we pass them. But if the forward iterator exists, and here we get to this interesting point. Sort of, do we really, this is what we're going to write, is the partition point. No, you don't. We will see, we do not. And what we, this is sort of where we go. This point, this algorithm finding partition point is, if you like, binary search. This something on which any binary search like algorithm is based. Right? Observe, we have nothing, no binary predicate. We have unary predicate. But nevertheless, we shall see it all works just wonderfully. And again, it solves the problem which have been bugging people literally for so many years. Right? First, it was bugging everybody till the first sort of correct algorithm was published in '62. But then even after that, it's been bugging people that because they still were coming with incorrect interfaces. They were returning, null or -1 when they wouldn't find things. And we see it's a bad interface. It's a wrong interface. So if we understand partition point, everything else will be very simple. And there is no ambiguity. This is right here. You do not return null, you always return partition point. The thing which sort of separates the false guys from the good guys. And the important thing is to remember that even when you have things like singly linked lists, such a thing is useful. Because if your comparison, if your predicate is very, very expensive, while iteration is relatively fast, you still could reduce the number of tests to log n. Right? And as we shall see, we still will have a very good bound on the number of traversal operations, which will be n, not order n, but literally n. And n minus 1, but that's besides the point. This is the question sort of which we need now to face. We want to write it in a such way that it first of all works for everything, and then it works for things like arrays much, much faster than it works for things like linked lists. Because and apparently it's a non-trivial thing. I mean, I was showing Paul and Hernan before the beginning of the class a message from a distinguished computer scientist asking me, what happens if we make it always linear, binary search? Will it really affect practical algorithms? Well, guys, the answer is yes, it will affect practical algorithms very badly, right? So we absolutely have to do it, that there is no performance penalty. So that's our goal, right? So let us figure out what's now sort of, let us figure out either the implementation or interface. Where do we want to start? Interface or implementation? Of binary search. No, we are not doing binary search. Partition point. Because if we do partition point, binary search will fall out of it. Actually, several binary searches will fall out of it. More than one.
We've already, I think we can do the interface at this point since we've discussed what you need to return.
Which range do we start with? There are two kinds of ranges. Bounded ranges, counted ranges.
Let's start with bounded. No? Counted?
Why? Which range is better for what we want to do?
If for implementing, I think a counted range.
Why? What are we going to be doing? This is why I always say start with an implementation, because you actually have no idea. All this idea, start with an interface, you have no idea till you see the algorithm. Always start with an algorithm. Again, I know that's not what they have been teaching you all your life, but I claim it's inside the algorithm, what you are going to be doing. You will be finding, okay, no. What's the algorithm for quickly finding partition point with smallest number of probes? Test the middle, bisection. This is the idea which is actually pretty ancient. Sort of the first, when Paul and Dye were investigating, the first idea of using it in sort of mathematical setting was by Lagrange, who applied it for finding roots of polynomials. That was around 1796, I think. And then sort of two people independently, as these two people invented a bunch of things independently, discovered it in sort of late 18 teens. First, Bernard Bolzano. Some of you who took the previous course might remember this guy from Prague, who invented lots of stuff. And then in France, by Augustin Cauchy, the French guy who also invented everything. So they were both invented the famous theorem, which is called bisection. Where do you bisection in mathematics? Value, yes. Intermediate value theorem. If you have a function which goes from negative to positive, it has zero. It just must. How do I find the zero? By doing bisection. That is a great idea, right? And then, as I said, Mauchly reinvented it in computer science context. So the idea is that we're going to be going to the middle. To go to the middle, what do you need to do? I mean, don't think profound thoughts. Think very simple thought. You need to divide by 2. And you don't divide iterators by 2. You have to divide in number by 2. So if you start with a number, it will be easier to keep dividing number by 2, right? So that's the idea. So it's better, it's a more natural interface to design partition point n, right? So partition point n will take an iterator of what kind?
Well, this one has to be a forward, I guess.
It has to be a forward iterator. But do we need bidirectional?
I don't know what the algorithm is yet.
Good answer. Okay, so why don't we do not say, maybe more, because he's correct. I know the answer, but we have to find it out. So again, this is why we couldn't even write type requirements, because it seems, it's actually, let me tell you, it seems that we need bidirection. Because, you probe in the middle, you either go there, you go there. Shouldn't you then march backward? The answer is no, as we'll discover, but it's not self-evident. The intuition that you need bidirectional traversal, you actually don't need it.
Well, I mean, if you remember the first one and always count, you can obviously do that with a very large number of traversals. So,
and you don't need to remember the first one.
You need to remember just the points at which you may want to restart your...
Okay, let us do first iteration of the loop. First iteration of the loop. So we start, what do we have? We have first, we agree that we have first. We agree that we have n. We have a predicate. So first of all, we need to get to the middle. For that, I suggest, let us start writing some code. Some code. So first, never mind, you already wrote in here. So let us call this midpoint integer half. It's a good name for it.
N half is equal to n by 2.
I wouldn't write it. I would say n half is equal to, I'm a penny pincher. I'm not going to use division.
Left shift?
Yeah, I'm going to use left shift, yes. Right shift, yes.
Right shifted by 1.
Yes. That I would do. Because, by the way, observe that one thing which we know is n is non-negative. Length of ranges tend to be non-negative. Therefore, shifting is all right, even if type n is sign type.
Mm-hmm. Then we just advance first that many times.
No, the other way. Like that. You could say, wouldn't compiler do it? Maybe compiler will, maybe compiler will not. Now compiler will do shift. There it is. So we figured out that is tricky. That is tricky. That doesn't work, sadly enough.
No, we should just do while.
First, let me tell you, I'm not going to torture you guys, then I'll explain. Because of things, advance does not return an argument. It advances the iterator. So.
Or we just call ourselves recursively or something.
No. Recursively in my class? No. While loop. My name is not Dijkstra. No, we will not do that. We will create first. Before we do that, we will, this line will say middle half, because I don't want to lose first yet. Hint. I might be willing to lose first, but not yet. I will sign middle instead of first on this line. Advance middle by half. Yes, therefore we need to define it. And what could it be? We have only one iterator position, so let's make it first. Yeah. And then we'll advance middle by half. Now we have something which is looking in the middle. Right? By the way, observe that sort of all of that would be really silly, absolutely silly and ridiculous, if n is 0. Just a pointer. That's the point. We will see. It's not an issue. You have to start writing code like that, but you have to remember that. So what do we do? Now we advanced it. Now we check. How do we check? If predicate, we need to apply predicate to middle. And then we need to think. Before we think, let's see that we have two things. I would say, if brace, closing brace, else open brace, close brace, so that we know where to put stuff. Now, so if the predicate is true, then what do we know? Then we could throw away everything to the right from that point on. We just throw away. This stuff is not interesting. So what we know, does first change? Does n change? What is it? Or middle is a pointer? No, it's not -1. It's literally half.
We've already tested that point, so we could.
It might be the answer.
Might be the answer. It might be the answer. Yes. I sense a go-to coming on, but you know, never mind. Or a while true or something.
No. Yes. Otherwise, if it's false, what do we know? Well, we could discount everything on that side. They don't, and literally everything. This is not the answer. Do you agree that if it's false, it cannot be the partition point? If I test it here, even if it's the last one, he is not the partition point. Therefore, what do? I discount him. So what do? I make first goes to middle, but I would go a little bit further than middle. Well, you know, since we live in this world of C++, I'll say plus middle. We moved it. And now what do we do with n?
N minus half.
It's a little bit. Here we're discounting a little more. We already got rid of one guy.
N minus half plus -1.
Whatever, it sounds correct, but I would say it n minus equal. And then I'll say half plus 1.
Okay.
And I would put it in parentheses, not because I need to, but because I'm concerned for poor reader of the code who cannot possibly remember precedence of operators and stuff like that. This is clear. And then this is it. Isn't that amazing? We need to figure out how, remember, this code is not even correct because we should guard it. What? Exactly. Let's put a guard here. Let us write here while n. As long as we're not at 0, we could go. This is really magic code, guys. This is.
Move the comment to inside the while.
And if n is 0, if it's an empty range, then it is a partition point. Well, both sides. These sort of. What else? I mean, you haven't got anything else to return at that point. When you fall out of while loop, there's only literally one thing you can return.
So we didn't need to be more than forward.
What? We don't need any more than forward. That's correct. It works for everything. Now, let's think about how many pluses are we going to do?
Well, n by 2 to start with, followed by at most, let's see.
sample n by 2 plus n by divided by 4 by 8 by 16. Yes, well, so it is a very tight, nice bound. Yes, compared with linear search, we're traversing more. Linear search on the average, in the worst case, it's the same. But on the average, linear search goes to the middle on the average. This always does, no matter what is, it always does, whether you're on this side, that side, middle side, it is going to. And another thing, observe, we are not trying to be lucky. Sort of all the codes which you'll find in textbooks will try to optimize it. Let's look at equality. And we're not looking at equality because there is no equality for binary search, because there is no equality. And for partition point, the point is well defined. It's this point. There cannot be any optimizations. The problem of optimizing here does not even arise. Okay? So this is if you are to know, okay, Paul has a good friend. And once upon a time, we had a lunch with his good friend. His friend is very famous, won Turing Award and everything. And he told us that there is only one algorithm programmers need to know. This is binary search, said he. And since he won Turing Award, I wouldn't trust him if you needed to program something. But that at least was, I'm not making it up. He did say that. One algorithm. I wonder how you get around without sort. Even if you want to use binary search. But I actually think I raised the issue during lunch. But he maintained that there is one algorithm needed only. I think he exaggerates, let me put it mildly, but at least even the guy who opposes to algorithms as useful things for programmers maintained that this is something very, very fundamental. Right? And you have to contemplate it. You have to try to really sort of get it. It's a very simple code. But now, let us figure out how we get from here to binary search. What? Oh, we need, I forgot. You don't know about advanced. Thank you. We need to figure out advanced, of course, I could tell, oh, this is very simple. Say std : advanced. But let us, I'll tell you how advanced works, because it is very important. Because while in case of advanced, you can just say std advanced. You need to understand the technology. Moreover, thank you. That was, I really appreciate it. Okay, so how does advanced work? Advanced was introduced by me specifically to enable us to do either long or very fast thing depending on the iterator type. Right? So advance is fast if your iterator is fast. In terms of pointer, it will translate into one instruction. It cannot be faster than one instruction. And this is going to be such an instruction, which is also going to be scheduled in parallel with other instructions. You could, so it's really like 0 instructions, right? So it's going to be very, very fast in case of pointers. In case of linked list, it's going to be linear time, because that's how it is. It's just the nature of the thing. And we have to see how it works. So let us write 2 versions of advance. We write a basic version of advance for input iterators. Therefore, it will work for all iterators. And we will write a specialized version of advance for, okay, this is, do you know how to do it?
You mean the type?
Type dispatch? Let me try. Because this does not require thinking, it requires knowledge of C++ thingy bobs. Okay, obviously C++ does not know whether a given type satisfies this concept or that concept. That is not in the language. So it will be one day after I die, I'm sure. But for for the meanwhile, we need to fake the mechanism. We have to write something which will do correct thing depending which complexity requirement are satisfied. Now remember when we covered iterators in the last lecture, we introduced the notion of iterator category. That for every iterator type, you could write this thing, colon, iterator category. Actually, you could write iterator traits, colon, iterator category, right? So at the top level, therefore, we're going, so let us write top level advance. The top level advance will say template, type name, I input iterator, the most general iterator type. Pardon me. Put N, yeah, type name N. No, type name capital N.
In this case, you could use different style.
In this case, maybe I even should use different type. Yeah, he's correct. We don't need N. We don't need N. I do not remember what's the standard interface. Why don't you to put N back, since I do not remember? Somebody, you do not remember? Okay, let's do it like that. It's easy to change. So void advance, it takes an iterator I by reference, because it's going to modify it, going to advance it. And it takes N by value. And then what it does, and it is inline, because this is inline, because we don't want this thing to exist. All of this code is going to be where this function generates no code. It's just ugly heck. No. What you write is advance. You write advance first, N, and then you write iterator trait, std iterator traits. This is a magic incantation to extract the type out of iterator. I'll explain, guys. I'll explain. Iterator traits, angle bracket, capital I, angle bracket, colon, iterator category. Open parent, close parent. It's hateful stuff, guys. I invented it, so I'm allowed to say that. Since, I mean, again, I'm trying to simulate language which understands things like input iterators, random access iterators, but language doesn't. So what we do is we just say, so what does this thing do? It calls the function, and here it passes an object of a type which designates whether it has random access long jump or not. Right? So now we have to write two versions, the general version and the specific version for random access iterators. So copy this code. Now we actually need two copies, but the two copies are going to take additional argument here, yes? And the additional argument is going to be std input iterator tag. That's a type name. Yes. No, it doesn't need a name. It doesn't need a name. We're not going to use it. We'll just use it. What? It's for the dispatching. And sadly enough, this is an empty struct. We're going to be passing nothing of different types. We use types as things for a switch statement. Yeah. Random access iterator tag, yeah, that's what it's called. Okay, and now let's write the code. So here, it's very simple. While n like that, but you need to say first, plus, plus first. Now say plus, plus first. Like that. That's, and the other one, first, plus equal. Plus equal, it's we're modifying. We're not returning anything. All right? So again, the question which was asked by somebody just a couple of days ago, whether we need all of that or whether we could always use this. Apparently, his student claims that this is good enough for most algorithms. His student is an idiot. This is not good enough.
Depends on the expected values of n.
Depending on the expect, yes. For n equal to 0, we don't need it, yes. If you iterate through empty things, yes. But even actually, if n is less than 3, it probably doesn't matter. But if n becomes big, yes, it does matter. Right? Do you understand how it works? So we call this. It expands into the other thing. Again, it happens literally at compile. This is not a runtime dispatch. This is compile time dispatch. It's either here or there. And it either does the iteration or does, there is an additional function which we need to know. There are two functions like that. One is advance, and then there is a corresponding function called no. No. The opposite function, no. It's called distance. There are two questions, right? Because again, distance is also. And I had, this was a design choice and complicated choice to which the answer is not simple. What I could have done, I could have allowed all iterators to have plus equal operator and minus operator. And of course, it would be for forward iterators, input iterators, bidirectional iterators, both of them would be linear. And my thinking was like that people have expectations that things like that are fast. So a person who writes this code would assume, he's not an expert on STL or anything, especially when I was implementing STL. I was the only leading expert on STL. Therefore, saying that is somehow becomes linear time will confuse many people. You could force them to learn the semantics of advance. It's much harder to make them learn new semantics of plus equal. I'm not saying I was right, okay? Because when we were writing elements of programming, Paul and I, we decided to abandon that and abandon advance and distance, and just say that depending on iterator category, the complexity of these operators change. Right? Now let's implement distance, since we cannot implement binary search today.
It's just greater than and equal or greater than call partition point. Or is it more than that?
It is a little more than that. But let us, okay, implement it at home. We'll talk about that. But the important thing, we need to implement distance. Because we would need distance to implement even partition point for getting n. For partition point n, you do not need distance. For partition point, the bounded version, you do need. Okay, so I recommend that we just copy all the advanced guys. And I'm pretty sure I was wrong, by the way. Guys, let's fix advanced. I'm pretty sure that the standard requires that instead of n, we use difference type. So let us do advanced appropriately. What does standard say? Apparently I did distance. Show me distance.
Class distance. It's just
No. Show me distance. Function called distance. Hernan, just quickly copy.
You want to hand that?
Yeah. No. I was okay. I know everything now. Do we have this? So let us make it. So change this to hoarded, just new line, delete void, and change advanced to distance. And we don't need type name, second type name. Just let's do the top level. And what we're going to be returning is std iterator traits. We need to extract a difference type from iterator type. Dependent type, difference type. You need to say type name someplace, like here, before std. I apologize again, but that's what we have to do. Distance, and of course, distance take first last, not first n. Not by reference. And then it says returns distance. Okay, I mean it's the same, it just does the dispatch depending on the type. And then we need two more. And in one, we're going to have a slow loop. And the other one, we're going to minus. Right. So copy, do two copies of this. Go to the first copy, add one more argument of the type input iterator. And now, of course, we're not going to be we need to change the code. And let us return the code here, change the code here, because it's very simple, the second case. Return last minus first. That's like, again, one instruction. When it's fast, it's fast. When it's slow, it is slow. But nothing we could do. So we did this. This, we have to write the same thingy bob as we wrote with type name line 125, copy line 125, and put it on 127. And call it n, and initialize it to 0, open paren, 0, close paren. Like that. And then you say while first not equal last, plus n. Plus first. And plus n. In whichever order you like, yes. Return n. Very simple. So these are two auxiliary functions, which sort of we will, guys, could I, one more minute, just to show the use. Now let us implement partition point without n. Let's copy partition point. Remove with template, you have to copy the whole thing. What do you mean it wasn't there? We didn't have it? Guys, we have to put it there too. Nobody's watching.
No, we decided to write the algorithm first. We didn't know what they did.
Oh, I see. Well, but we still need, we have to finish it.
We don't have any.
And then what you do, anybody wants to implement it? Guys, you say return.
Return partition point n first, comma, distance first, comma, last, comma, pred.
Right. So I just wanted to show how it all fits together. Now, right, have we finished? We have to correctly finish this stuff. I know how we will do it. I'll do it. I'll just finish this stuff because I already have all this stuff correctly done. So I'll just move the file on top of this file. So it's cheating, but you have to cheat occasionally. All right, guys. As usual, we're running out of time. Hopefully to see at least few of you next time.